time I'm going to talk about the model selection, parametric model, non-parametric model, and the big Gaussian process. Continuing in the topic, Sean talked about last time. We have, for example, we have the logistic regression or linear regression. We have a model y is equal to W transpose x. X here can be in the equal space, or you can transform to another space, which called feature space. For example, here we choose x to be x squared, x cubic, xn, maybe minus 1. So they are totally terms. And because the length of this vector is n, so the length of this vector should be n2. So there are n parameters. Omega w is equal to w1 wn. So if you take in the product, it's like w1 times 1 plus w2 times x. So you take like summation, which is equal to y.
Why the first one?
The first one? First one, you can think of it as x0.
Oh.
Or, well, you can, sometimes people call it bias. So, which moves your, like, x, y up and down. And one problem here is how many terms do we need? So we should keep like 5 terms or 100. For example, if you have a data like this, so how many terms do you need to use? By the way, this is called model selection. So one way to model this is what? Maybe I can just ask some questions. How to choose this n according to this data? We can choose, for example, if we just choose like 2 terms, in that case, this is equal to y ax plus b. If you only keep 2 terms, this is going to be a line like this. In this case, apparently, the proposed model cannot fit the curve at all. Or we can choose a very high order, maybe 5. So we are going to have something probably like this, which can pass all the data points. That has a very low rooted mean square error during training. But during testing, there probably is not a good model at all. So, given this problem, so how do we choose the model? By the way, the model here, it's not talking about if you should use this linear regression form, or you should use a supervector machine for regression. The model here is not like that kind of level of model, but a particular hypothesis here. You have multiple models inside this hypothesis. So the model term is a smaller term than the general model. So how do we choose the certain model in this context? boring. Actually, I'm going to stay here. Any thought? Anything is fine. Okay, so one way to do this is less mathematical, but in practical used very often. One way to do it is called a cross validation. Well, the problem here is model selection. Say we have an entire array of training samples here. And instead of arbitrarily pick up a model, for example, like the 5 terms, and train the fixed model into with this training data, we can use cross validation, which divide your array, like the training samples, into and fold into what, like n folds. So each time we train the model on, for example, this is reserved for validation, to validate how good is your model 5. Each time we leave out one section and train the model on this array. And then next time, because by picking up these sections, we might get lucky or unlucky. Well, if we pick some value which is potentially easier to regress, then then the performance is actually better than the reality. Or we can get unlucky. We pick up some tough questions here, so the model behaves really bad, but actually it's not that worse in the reality. So here, instead of picking up only one section for validation, each time we pick up one section for validation, and each time we switch. And next time we use this section for validation, the rest for training. So after like n times, we get a performance evaluation for this model 5. But the 5 is not necessarily the best one. For this, I might choose a lower, smaller model or smaller model. Maybe I just choose 2, and then I run the same thing again to see if the model trained performs good on the validation data set. If you have like multiple models, you just do this process for each model and compare them. And this is almost the best you can do, given you only have a small amount. You only have training data. Because test data, it's just unknown for you. You can just hope for the best. Given this training data, you can evaluate each model and hope they are going to generalize while in the testing data. So that's why probably sometimes you need more training data, because the more you have, you have high chance of generalize your model well. And another way of doing the model selection is actually the Bayesian method. Bayesian model selection. Here, if you think of this formula, you can write this as x, y, given x and the parameter w. And actually, there is a kind of hidden variable here, because before you even train your data or train your model to fit the W into the data, you choose this model parameter for models, and you can call these parameters like M. Well, this M can be like 2, 5, 6, or whatever. So you can think this as another set of parameter, but people don't usually call it parameter. They call it hyperparameter. So in Bayesian model selection, Bayesian model selection is very similar to the Bayesian approach when for like Bayesian methods. In Bayesian methods, if we are going to make a prediction and the data, we are going to first we are going to write down the posterior probability of the parameter, and then we are going to make the prediction with that certain parameter, and then we kind of like integral over all possible parameters. And for the Bayesian model selection, well, the first part is actually averaging. This is like parameter averaging because you have a posterior distribution of parameters. When making prediction, you want to average all possible parameters. And in the Bayesian model averaging, you have an extra parameter which is like hyperparameter. And this is equal to, let me see, y given data model and p model given data.
So what's the difference between x and p?
X here is here D is this. This is training sample, and if I get a new X, which is like when you're testing a model, so this is like unknown, you need to predict. So you need to average our model given the data. They are actually very similar. I missed the term. X. Yeah. So the idea is just being basic. It's not anything fancy. And this term actually is this guy. So they are the same. This is Bayesian model averaging. So given data, the distribution of the model probably is. I can just draw arbitrary posterior distribution of a model. So this is this is different value of models, maybe 1, 2, 3, 4, 5, these values. And given the data, the posterior distribution of the model probably is like something like this. So still, this singular model are, well, for example, are highly likely. This is the density function of the model probability. So you have a higher tendency of choosing a small, like simpler model. Well, you have very low probability of choosing a very complex model. So when you average all this, you you are probably not going to overfit like this line does.
What's the?
D is the training data.
And you just write it down this one using this equation.
This, yeah, this equation is this guy. Yeah.
Yeah,
And,
just M as a one of the.
yeah, this is your model, and this is the your hypothesis. This is the model. Yeah, and this is the probability of the model parameters. This average these parameters, and just like this guy, we can do a point estimate using MLE or MAP to simplify this problem. Because last time, as we mentioned, this integral is often very difficult. And actually, probably no one is actually doing this because this is often very complex to compute. And to simplify this, we can use a point estimation. And instead of using a distribution of this guy, we just choose a model parameter which is most likely given the data. This is the maximum likelihood estimation, or given a prior, the posterior distribution. Well, the model is here W can either equal to R max P D given W. This is a maximum likelihood, or you can use P W given D. This is the map. You can use this two ways to estimate your W. If we have fixed model. Here we can do the same thing. We can either use the maximum likelihood estimation for M. So M is equal to argmax PB given this, or the same PM given D. Sometimes this is called model evidence. This is like point works. We can call it point approximation of this guy. So if we do this, we select a particular model already, because M will probably, well, for example, 3 can be the M get from this formula. All this we talk about is parametric model. In parametric model, we need to do model selection. But there is another, not completely different, but very different thought on this problem. Instead of parametric model, we can use non-parametric model. Is there any? Anyone can talk about any like non-parametric model they have a thing or?
Yeah.
EM, okay. Non-parametric model. Let me see. I tend to call this algorithm for solving the model. For example, if you have a key, what do you call it? Wow. We call it there are mixture of Gaussian, yes. I'm not completely sure about this, but I kind of think this is an algorithm for solving this type of problem. So this problem actually, you need to choose how many Gaussians in the mixture Gaussian. You either choose there are 2, 3, or 4. So there are k Gaussian. This k here is similar to how many terms do you want in your linear regression. You either have 5, have 3. So how many of them are there actually? Because if you choose different k, you can have a different fit of the data. Actually, the more k you have, the better it will fit the data, because eventually you can have one Gaussian for each data point. Yeah, this is the parametric model, and this is parametric, and here we have the linear regression is parametric. Well, SVM is parametric. Well, neural network is actually, after this neural network is parametric because you need to choose how many layers, and each layer how many nodes do you have. Well, actually, a lot of algorithms are parametric model algorithms. So for parametric model, you need to somehow find the best model. And there are some non-parametric model. For example, when you do regression, the same problem. So if you have this data, if you want to fit a parametric model into this data, which means you have a form where for any form is fine, phi x, let's see. And we need to fit the model to the data. And then after fitting the model, you have a fixed parameters. You have a W, it's given from the data. And then when you do testing, you are going to throw all this data away. You only keep the parameter. That's you assume this is all you can learn from the data, given the chosen model. And another way actually to do it is instead of throwing away all the data, let's keep it, because I don't know what model is better for this problem. So let me just keep it. And next time, if I get the input x, which is unknown, I don't know which value it should be. I just find the x in the training set, which is close to the input x. Well, we can call it neighbor of x, which is close enough to the x. And for example, right now is this a few data points, and then we can fit a straight line here. So for example, this is x. We fit a straight line here. Then you know, okay, because these x are close to my query point, so I think even though they are kind of linear, fit the data, I can still think this is better forecast. This is called what do you call it? Locally weighted regression. Curve regression is similar to this. I think there are differences how you measure the distance between input points. So the big difference between parametric model and non-parametric model is that non-parametric model, you have an infinite amount of parameter instead of a limited amount of parameter. The non-parametric doesn't mean you have no parameter. Actually, it means you either have an infinite amount of parameter or your number of parameters increase with the number of data. Actually, here you can see if we have more data, I can use this extra data to compute another line if I need to query here, which means you have more things to feed. That's why they call it non-parametric, and because this data is like a parameter. Go back to the Gaussian process and the Dirichlet process. Gaussian process is actually someone call it if you have a infinite amount of terms here, this is equivalent to this. And I didn't really go to what do you call it? Well, the proof we went through last time is kind of similar, showed this result. So Gaussian process is is like infinite terms version of the linear regression. So, by the way, this method are kind of old and not many people are using it. And Gaussian process is a bit harder now. Or there's another model called the Dirichlet process. I think this is more for regression or classification. And this gives first impression. I'm not sure. The Dirichlet process, I think it's more for the more for it's for unsupervised learning. And sometimes you. For example, you have a mixture of Gaussian. You use the Dirichlet process to model mixture of Gaussian. Because it's non-parametric, you don't have to specify the number of Gaussians beforehand. Somehow it can adjust the number of k according to the data, but I didn't really go to the detail. Is there any questions? Then I can show some example of Gaussian process.
is on that one?
Yeah, this
Yes. Okay.
Oops. For that.
Yeah, thank you.
Yes, for that computer. It shows that computer. It shows that this computer.
Not this one.
Not
Yeah,
this
this
one.
one.
How do you try to? How do you?
Yeah.
So yeah, this is well, I found this online. Demonstrate the Gaussian process.
Okay, please begin.
I don't know.
Right.
You see here we can make some input. This is more like a training data. Then you can choose your kernel. It's very expensive. This is a result of fitting up data. Like we talked about last time, it's like a combination of conditional probability and the marginal probability. If you want to query this count here, you have the input. You want to know what's the value of this guy, the corresponding y. And because you only have this amount of data, okay, I can make some prediction, but I'm not going to tell you, okay, this is the value. I'm not going to tell you that. But instead, I'm going to tell you a confidence region. Given like 95% of confidence, I'm going to tell you the value is going to be in this region. You can always ask me, is it possible, given this value, I get a y here? Well, the answer is, yeah, this is possible, but it's very less likely. It's always a probability distribution. And when you are confident about your prediction, for example, you have enough data point here. If I query this, well, what's the corresponding y of this x? You are going to tell me, okay, because I have observed enough of value in this region, so I think I'm very confident it's going to be in this region. So, and the next time if you observe more here, and then it's confident, oh, this region is smaller now. So I know the true value has a 95% of chance inside this region. And if we make some point here, it's kind of obvious. Yeah, this is the one good thing about Gaussian process. It always gives you a distribution, and the distribution is easy to compute. Well, with other algorithms, you can compute the distribution, but again, the computation is going to be complex, and either it's approximation, or either you approximate an exact problem, or you solve the approximate problem is the exact solution. So it's always some trade-off. But Gaussian process gives you a nice balance between your accuracy and your complexity. You can play the and because Gaussian process is one kernel method. The kernel is used to compute the covariance matrix. So you can choose different kernel to compute the covariance matrix. You can choose this. You can see actually this is repeating this part. This part actually is this part. if you have some prior knowledge about your data, you know it's generated by sine or cosine. You know it's going to be periodic, so you choose a periodic kernel. I think there's definition. Well, yeah. I think this is the definition of the kernel. You see here the sine. So you scale it and do something, and you get this result. And you can, well, there are other polynomial values. So, let me see. Here, actually, it's called non-parametric, but still you can see there are some parameters for the kernel. For example, how far are these 2 points away? Is it like far away? They don't have any correlation, or they're actually very close? This is on the scale of the x-axis. You can imagine this as like moon. This is like Earth. They're pretty far away, or you can imagine this is a molecule. This is another molecule close to it. So they have different correlations. And then you have to somehow specify the scale of your parameters correlations. If you, for example, if you change it
Take a minute.
what was that?
Front of that. Take a minute.
Oh, calculate, yes. Well, maybe it's too small. You see, there's high variance compared to that one, because right now you zoomed in the curve. So, well, yes. So, and you observe this guy, that really tell you a lot about the rest of the point. So you see it's almost unpredictable for this. But if you zoom out, well, everything is predictable, because you are now assuming these 2 guys, even these 2 guys are very, very close. So they have very strong correlation. So you observe this one, you know what's going to happen to that one. So there are other parameters. You can change the magnitude of the y's by using this guy. You simply just times it. It's like either like very big, very small. You can control with this. This I think is more or less. Well, it shifted, but somehow I saw this term in to model the noise. I think maybe there's something to do with it. And another interesting is, well, in Gaussian process, the kernel are used to measure the similarity of inputs. And well, other kernel methods is the same. So super vector machine, how do you measure how similar are the inputs? Well, if your inputs are the vectors, okay, you can somehow at least compare. But what if your input is a graph? So which doesn't necessarily have the same structure. One maybe have 1,000 nodes, another maybe have 1 node. Or maybe your input is like a string, a text. So if you want to say if this news is close to that news, they have different length. How do you measure the similarity? So there are different kernels for it. Like for the text, for the text, if you want to compare the similarity of text, you have a kernel called string kernel. And if you want to compare the graph, there are some other like kernels which is much more complex than the vector word. And there are, I think there are quite a few online resources, and there are source code in R, in MATLAB, in C++, in Java. yeah, and I haven't tried. Maybe if there are some problem can be solved by Gaussian process. Maybe using these libraries and quickly experiment the result. What else? Yeah, there are some interesting computation for kernels as well. So it turns out you can, given two kernel, you can somehow combine two kernels to get a new kernel. You can take a linear combination of kernels. I think you can even multiply kernels. I don't know if you can divide, but you can somehow compose kernels into a new kernel. And these kernels should be a positive definite, semi-definite. Yeah, actually kernel is more general than this Gaussian process. What else? Is anything we can discuss? Well, oh, by the way, so for these parameters, even though they are called hyperparameters, this P1, P2, P3, P4, P4 is not here. It's not in this formula. Someone is using maximum likelihood to learn these hyperparameters as if they are parameters. If you want to learn these hyperparameters, then it goes back to the Bayesian methods again. Because for these parameters, you can either take point estimation of particular P1, P2, P3, which give you a highest likelihood of all the posterior distribution, or you can average all possible values of these parameters, just like Bayesian methods. I don't exactly know which method is better. But maximum likelihood or MAPs always have a tendency of overfitting. Averaging probably is better, but I don't know if it's a complexity or computational complexity is high or not. Yeah, that's all I can think of. Any questions? This example is more like 1D. You can have a high dimension as well. So just like you can have a high dimensional Gaussian distribution. So it's the same thing. There are other model selection methods. I'm not really clear. One is called AIC, another called BIC. I don't really go into that. Last time when I was in library, I just saw a whole book on basic model selection. Whole book. I think it's a deep topic. Yeah, that's more or less it. Okay. Well, another thing is here, if you compute the covariance matrix with this function, and you need to inverse it, and if you have a high or a lot of input data, it's going to cost you a lot. So there are some papers on how to simplify the computation. There are all sorts of points in this process you need to improve or change. Okay, that's it.